Oi, let's talk about cosmology. Like I was saying, apparently the universe is infinite and expanding infinitely. In order to explain this, astronomers, astrophysicists, and other astroscientists have come up with something called the cosmological principle, which basically says that the universe is homogeneous and isotropic. And this principle is intended to apply on the largest scales, which is what cosmology is. So, the isotropy is if you look out in any direction, you're going to see the same patterns. Homogeneity is wherever you look, you're going to see the same pattern. Homogeneity would mean if you went to somewhere else, if you moved your location, you would see the same sort of thing. Whereas in isotropy, you don't move your location, you move your perspective around. Those two proposals make up the cosmological principle. The universe looks the same wherever you are and in whatever direction you look. In order for this to be true, the universe has to be infinite, because homogeneity doesn't work if the pattern doesn't extend infinitely in either direction. Isotropy can work in an isolated space, but homogeneity extends infinitely, and then so if it's both isotropic and homogeneous, then the universe, basically, if you have a grid, this is not completely accurate, it's an analogy. If you have a grid, a two-dimensional grid of little squares, then the grid extends infinitely in all four directions. What does this mean? It means the universe is infinite. And as I was explaining before, it's expanding, so it's infinite and infinitely expanding, and that's space-time for you. Weird. Again, this is on the scale of clusters and superclusters of galaxies. Not even on the galactic scale. It's on the intergalactic scale. So, yeah, big stuff. Isotropy is testable to the point where, just by the fact of our own observations, we're pretty much positive that the universe is isotropic. But by its very nature, homogeneity, it's not testable. One, we can't go anywhere else yet, especially on the scales we're talking about, without wormholes or some other kind of subspace travel or faster than light travel going to other galaxies, let alone other clusters of galaxies, is kind of a preposterous notion. Even if we were able to do that, though, too, the universe is infinite. Goldbach's conjecture. It is a unsolved mathematical problem, Goldbach's conjecture. It states every even integer greater than 2 can be expressed as the sum of two primes. Now, the problem with Goldbach's conjecture is that numbers are infinite. So even if by everything we've seen so far, it's true, we can't say it's true. Because numbers are infinite, we cannot possibly test all of the numbers to prove that every even integer greater than 2 is the sum of two different prime numbers. Also, you can't disprove it. It's infinite. And so, that's why I think it's better to think of homogeneity in our universe as calculus. And by that, I mean it's better to think of it as approaching infinity. Calculus, at least that part of calculus, is all about talking about how numbers seem to be as they approach something. Because there's a lot of those, exponential curves, and that curve, it's logarithmic curve? Can't remember. All those curve things that do fancy, fun stuff to look at in graphs, all of those are dealing with the approach of a number, where numbers do interesting things. And so I think the cosmological principle, when it comes to homogeneity, is really trying to say that approaching infinity, the universe appears homogeneous. However, the cosmological principle can't say that. So it's like Goldbach's conjecture. So the cosmological principle, when it comes to homogeneity, is fundamentally unprovable. However, it still helps us as a model of the universe, the same way being able to say that something approaches something else and behaves in this way as it approaches that helps us with calculus. It does stuff for us, man. Yeah. So, there's some value in it. However, you must tread lightly when you're talking about things in science that are untestable. So, earlier, I talked about a grid. You know, the grid. It's expanding infinitely in those directions. Well, frankly, our universe isn't a grid. It's more like a sphere. If I ever start talking about positive curvature of space-time, which is a lot, that's talking about, like, I don't know. I don't even know how to. Okay, I'll get to that. The universe is like a sphere. Wherever you go on the sphere and you look, everything looks the same in every direction. There. And you can be inside the sphere and look out, and everything looks the same in every direction. I think that's all I have to say about homogeneity and isotropy. How does this relate to expansion? Oh, I'm going to have to talk about that in a different video.